Hello. Okay, section 3.4, equivalence relations. Okay, there's a lot of important ideas in this section here. So, okay, let's just go through these things here. The theorem. Okay, so what's a partition? So, let S be a partition of a set X. Okay, so a partition, think of it as you chop it up into distinct sets where, well, I guess that's here, where there's no two elements in common and things of this nature. So if you have a partition of a set, then if we define x r y, x is related to y, to mean that for some set s in x, s in s, both x and y belong to s, okay? Then R is reflexive, symmetric, and transitive. Okay, so let's take a look at just the proof to remind us what these definitions are here. So let's let X be an X. So by definition of a partition, X belongs to some member S of capital S. So it's X is in some set in the partition. Thus, X is related to X, right? Since R so R is reflexive. And suppose that X is related to Y. Well, then both X and Y belong to some set S in capital S, script S. Okay, since both Y and X belong to S, well, then we have Y is related to X, and so R is symmetric. And finally, let's suppose that X is related to Y and Y is related to Z. Well, then both X and Y belong to some set S in capital S, in script S, and both Y and Z belong to some set T in script S. Well, since Y belongs to exactly one member of S, that's the idea of it being a partition, then we must have S equals T, and therefore both X and Y belong to S. And so X is related to Z. Okay, so therefore we see that if you're given a partition, then you get yourself a reflexive, symmetric, and transitive relation. Okay, so such a relation has a special name. So a relation that is reflexive, symmetric, and transitive on a set X is called an equivalence relation. Okay, and equivalence relations are important in mathematics. Okay. There's a bunch of examples you can look through here. And here's a nice theorem. This is really, really a nice theorem. It says, let R be an equivalence relation. So if you have an equivalence relation on a set X, and for some A in X, let this bracket A be equal to the set of all X such that X and X, such that X is related to that element A. In words, that symbol is the set of all elements in X that are related to A, right? Then script S, which is equal to the set of all such bracketed things A, where A is in X, that is a partition of X. So partitions of X and equivalence relations really are the same thing. Okay, and I'll let you go through the proof. Definition, let R be an equivalence relation on X. The set A, right, defined in that theorem, that's called an equivalence class of X and is given by the relation. Okay, so where this is really important is in this one example here. Let's look at this example here. It's really here. Let's just look at this example here. So in example 3.4.4, we showed that the relation R on the set X equals this is an equivalence relation. So here, the equivalence class 1, right? What is that? Well, that equivalence class 1 contains 1, right? And so what else does it contain? Well, because of this and this and this, and well, it means that it's the equivalence class of 1 is the 1, 3, and 5. So there's those three things are in the equivalence class of 1. They're related to each other, and yeah. So that's the equivalence class, okay? Equivalence class of 3 equals equivalence class of 5, right? Equivalence class of 2 equals equivalence class of 6, right? And the equivalence class of 4 is equivalence class of 4. Okay, where does this come up in our many practices here? Well, let's look at this here. Let's look at this example. Let X be the set of elements 1 through 10. Define X is related to Y to mean that 3 divides X minus Y. Okay, now we have to check this out. We can readily verify that the relation R is reflexive and symmetric and transitive. Thus, R is an equivalence relation at X. And it says determine the members of each equivalence class. So the equivalence class of 1 is equal to the set of all X and X such that 3 divides X minus 1. So that's equal to, let's see, 1, 4, right? 7, because 7 minus 1 is 6, and 10, because 10 minus 1 is 9, and 3 divides that. Similarly, the equivalence class of 2 would be these numbers, et cetera, et cetera. Okay, so let me show you a very important, very, very important theorem here. And it's very obvious as well, but here, let R be an equivalence relation on a finite set X, okay? Finite set X. If each equivalence class has R elements, then there are the size of X divided by R equivalence classes, right? You can see that because that's the only way you could divide up, n finite number of things so that they have the same number of elements in each equivalence class is if there were that many of them. And the way you can see that is here. Let's let x1, x2 up to xk denote the distinct equivalence classes. Since these sets partition X, in other words, chop it up into mutually disjoint sets there, then you have the size of X is equal to the size of X1, size of X2, all the way down to the size of XK. But we're given as our hypothesis that there are R elements in each equivalence class, so that'd be R plus R plus R, so that'd be K times R. And if you divide that equation by what? By R, you get K, and that's the number of equivalence classes because it's a K right there and it's a 1 right there. Okay, so that should be enough for you to do all these problems in 3.4. It's just a lot of definitions and these are very important. So I hope that helps out. Thanks.